breaking the wall of quantum cinema. How high-speed X-ray lasers will allow us to make life reports from molecules at work and from chemical reactions. Helmut Dosch, Deutsches Elektronensynchrotron of Helmholtz.
When the wall came down, I was in Munich in a bar. It was an unbelievable atmosphere. We all had the feeling that we were witnessing a great event.
So what I would like to invite you is again a travel into the nano world, right? So you have to be a little bit concentrated here. So at the end of my talk, I will present you, so to speak, a high-speed camera, which should allow us in the next decade to make movies like this, right? These are two water molecules during springtime. And we would like to see how bonds break and how they are formed. So why we are interested in that and what this would be the benefit for that, is the topic of this short presentation. So we talk about movies, we talk about cinema, so the whole talk is made as a movie and it starts in the same way, right? Where is it going? Yeah. So let's go into the nano world. You know, there was one wall which was broken almost now 100 years ago, more than 100 years ago by Röntgen, who discovered the X-rays, which actually were the tool at hand, you know, to get really into the nanospace. With this one, you know, you could do this breakthrough experiments, which is actually almost 100 years old now, namely this famous experiment by von Laue, who took a X-ray tube and put a crystal in it. But we heard about that a couple of seconds ago. And what he found for the first time, you know, this is a photographic film, and he saw this interference blobs. This was the first signal ever for mankind that atoms exist. And they came from this crystalline structure, and it opened, so to speak, this interference pattern, our eyes for a new length scale, namely the nanometer length scale, so which is the distance typically between atoms in every structure you see around you. So what is nanometer, right? So we have been living in the millimeter range. All of a sudden we have to go to the nanometer range. This is this incredible small number. And to visualize that for those of you who are not working every day in this length scale, so the Earth is 13,000 kilometers long. This is a forbidden currency, as you know. So the penny is 13 millimeters across. So if the Earth would shrink to a meter, now the penny would shrink to a nanometer. So this is, roughly speaking, the challenge one has in order to go to this length scale. So this happened 100 years ago, as I said. And so the quantum theory was developed, X-rays were developed. You see again this interference pattern. If you reflect what was at that time the most, you know, impressive technological achievement. Some people think it was the Eiffel Tower at that time. So it was built out of many, many bolts, was 300 meters high. This was the architecture of that time. Now, after this discovery, we live today. So our world has changed completely. Now we are dominated by discoveries which are made in the nano world, so from medical to information technology. Here, this is the Pentium processor, which has 30 million transistors on a square centimeter. So this is what we have today, and this all goes back to a discovery which has been done 100 years ago. So to illustrate that again, you see here a scenery in the southern part of Europe during lunchtime, and you see that these people are enjoying themselves. So they would not be able to do that if not many, many smart materials are working every nanosecond to make their life pleasant, healthy, mobile, communicative. You see that here. These are the materials which are doing work every day, right? Every second for you. So you can see from this discovery of the nanometer range, we really profited all enormously from it, right? So it would not be, this world and this technology would not be possible without these discoveries. So the question is, now, we would like to improve everything, right? We would to have better medication for vexing diseases. We would have better materials for transport and energy. We need better communication technology. Question is, how can we make now a step forward? Now, we are facing a limit. Now, this is the topic of this talk. So, the question is, which is the next wall to fall here? When I illustrate this to you with a comparison, reflect back in the early months of this year, we had the World Championship 2010. Imagine we are watching this game now. Now the game is on. The two teams are on the here out, and we would like now we see the game, right? And now imagine the following happens. This you see this, and the next what you see on your screen is this. It's a wonderful result, right? It's wonderful. So we love it, right? But we missed something very, very important. We didn't see the game, right? We didn't see the match. So it's fine with us, right? The result is fine. But we don't understand what's going on. We don't know how the whole thing evolves. We even don't understand the name of the game, right? So this is terrible, right? But this is the way how we understand nanoscience at the moment. I give you an illustration. You know, a very simple chemical reaction. So you take the two, this is Germany, this is Argentina, right? And this is the result. This is roughly speaking. Okay, so you put them together and here's the result. Now what's happening in the chemical reactions as we can do it today is this, right? Here, and we create H2O. Yeah? So this is all we see. So what we are missing is, of course, you know, how does this reaction evolve in real time? We want to see how they bond together, what's going on in detail, and if we can see that, can we identify, so to speak, transient states in between? Are they trapped in intermediate states and so on and so forth? So in other words, we would like to see this, right, in real space. Right? We want to see the game. Here, that's a famous one, Germany, England, and you see here's a transient, that's a transient state. Yeah. Yeah. Is it? And you can see very clearly it's no goal, right? And that's also a contribution to the first talk, which was dealing about Schadenfreude. You remember that? So you see, in order to understand such a dynamical process, you really have to understand this with the necessary spatial and temporal resolution. For the soccer, it was milliseconds and millicentimeters, right? If you have that. So this is what you need. So 50 milliseconds should be sufficient. Usually the referees don't have that. Therefore, they make these interesting decisions. So in the nano world, it would be this, right? We would like to see in real time how this is a nickel nanodot, how this is oxidizing in real time. So that's a very costly computer simulation. It shows the oxygen molecules approaching the surface and then oxidizing here the nanodot, right? And you see here the time evolving, PS. It's no energy, it's picoseconds, right? This is how it evolves. And you see here, here's the soccer time scale, 50 milliseconds. And now if you want to go to this time scale, you have to move to the micro, to the nano, to the nanosecond. It goes to the picosecond. It's not even sufficient. You have to go to this unbelievable time scale, which is femtoseconds, right? That's the nano world, right? So that means if you want to follow that in real time, you have to first of all have the necessary spatial resolution to see this. You have to see the atoms, and you have to be so fast that you are faster than the atoms move. So you have to make a camera which is as fast as femtoseconds. What does femtoseconds mean? Like comparison, velocity of light, breathtaking velocity, 300,000 kilometers per second. So this is the distance to the moon. If you switch on a candle here in 1.3 seconds, chuck, now it's on the moon, right? So another experiment. You know this person in Berlin. So if you take her hair, and this is typically 50 micrometer, and you shoot light through it, no, it was too fast for you, right? Here we go, right? So then you see this is the difference. If you make a subtraction of it, then you find out it's 200 femtoseconds. So that means we have be so fast that light in the time when we are observing is only traveling across the thickness of a hair. That's the challenge of it. So that means this is what we need, right? The dream of mankind. We would like to make real-time holograms of the motion of atoms and molecules and electrons in order to understand matter better. So this is a droplet and moving, so we have to have two walls, in fact, to break. We have to create a laser because we want to make holograms in the X-ray range, which has not been done before. And we have to take pictures faster than atoms move, femtoseconds. The question is, can we do that? The answer is, yeah. Okay. And this is the camera, right? This is the camera which is currently being built in the Hamburg area. So it's a strange camera. So here is DAISY, where we are working. So we are constructing a relativistic electron gun. And here is Schleswig-Holstein, right? So we are shooting from Hamburg to Schleswig-Holstein. So with a superconducting accelerator, and these electron bunches now are hitting here particular magnetic structures, which convert these electron bunches in X-ray flashlights. And here we have then the experimental stations where we can make the movies, right? That's the way how it goes. So this is an enormous enterprise. So you see, again, from the DAISY side, here is the injector building, and you see here on top, this is then the accelerator which is built underground. It's working with at minus 221 centigrade. So we accelerate up to 7 billion electron volts. And here's the electron, the magnetic structure. This is the flash, right? And if this flash is produced, then we can make exposures of the molecules, right? And then we create the molecular movie. So that's the way how it goes. So this is a big microscope we are building. So it's a multinational European exercise. So many nations are joining us here together to build this in this very second. And this is the benefit of that, right? We would like to see the nanoworld in real time. For example, we would like to have better computers of the future. So then our future computers should not switch off as we switch the computer, but keep the memory. So we would like to have non-volatile memories. So the name of the game is to find out how a magnetic nanodot switches in time as fast as we need it, because you have to address that. So this is completely unknown. A lot of experiments are going on, so you have to switch it with this frequency if you want to address that with the CPU frequency of your computer. So this is an important technology of the future. Even more important for energy is that we have to control catalytic reactions better. So this is our catalyzer. So which here is the CO, the NO, which comes from your motor. Something is switching here all the time. Now I have to go back. That I switch on the movie again here. So you see, here comes the CO, the monoxides in. So you have here the oxygen. The oxygen gets dissociated at the surface, and then the oxygen atoms are then oxidizing the CO. So in order to understand this catalyzing reaction, really, you have to see it in real time how these motions are, because the CO reaction depends sensitively upon the surface reaction of all the other atoms here. So that means even catalytic industry who are building catalyzers tell us nowadays that they would like to see that in real time. So that's the challenge what we have. But also for better medication, such a time resolution is, of course, the way to go. So we would like to understand now in infection biology, now how are the first molecular reactions when you get an infection, that one can actually create better medication if one understands that in a better way. That's all I wanted to tell you. You see, this quantum cinema, it's not only a nice toy, but it's also an advanced technology that we can really develop better drugs, that we get more efficient energy, and that we get more better material for our knowledge and technology society of tomorrow. Thank you very much.